Thanks very much for coming. It is my great pleasure to introduce today's speaker briefly. So Professor Alberto Saa, he did a postdoc in Santiago de Compostela in Spain and at the Freie Universität Berlin in Germany. And after also several stays in research stays in Barcelona, Zaragoza, Valencia, and the Université de Bruxelles and Caltech. He is currently a professor of mathematical physics at the University of Campinas in Brazil. Without further ado, thanks very much.
Okay, thank you, Alex, for the introduction. Thank you very much, Professor Lemos, for having me here in this wonderful place. I will talk about Robinson-Trautman solutions in 2+1 dimensions. I started to talk about this topic in the CENTRA seminar, but we have 5 minutes, you remember, so I have more. Today we will have more time to go deeper in these things. This is the outline of the talk. I will recall briefly what are the Robinson-Trautman solutions, their relevance in general relativity. They are intimately connected with the Calabi flow. That is one of the geometric flows that mathematicians have studied in the last 50 years. And then I will talk about Robinson-Trautman arbitrary dimensions, and we will see why in n equal 2+1 we have a problem. Then my contribution is to propose what would be the equivalent of Robinson-Trautman evolution in 2+1 dimensions, and this is connected with a mathematical problem of plane curve deformation. And I will finish with some remarks. I think it stopped work already.
Oh, it did. Oh, then.
No.
So you have to really press really hard.
Let's start recalling what are the Robinson-Trautman solutions. This is the standard material you can find, for instance, in this book. The Robinson-Trautman spacetime is a spacetime where you have expanded congruence of new geodesics with no twist and no shear, and they are VAC solutions. These conditions of having this expanding congruence of new geodesics without shear and twist is enough to write the metric in this form. It is not difficult to derive this form. You have a congruence of new geodesics, so you have a tiny light, a new light coordinate is u, and you take one perpendicular, that's r. And it's not difficult to see that the metric has this form. Robinson-Trautman spacetime are vacuum solutions, so they are weak flexible solutions of metrics with this form. Q is an arbitrary function. I think that I prefer to use this. Q is an arbitrary function. K is not an arbitrary function. It's written in terms of Q by this expression. This expression has a geometrical meaning. That is the connection with Calabi flow, by the way. This expression corresponds to the Gaussian curvature of the submanifold corresponding to R equal 1 and U constant. So this is the Gaussian curvature of this part of the spacetime. Okay. The condition, the reed flat condition, implies this relation between Q and K. This is a parabolic equation, parabolic-like equation, because it's first time in the U direction, but the right-handed side is nonlinear, fourth dimensional, so this is not parabolic in strict sense. It's parabolic-like.
So it is an equation for Q.
For Q, yes. For Q.
Because K is the definition.
K is the definition for Q.
Q is an equation for Q.
Yes, Q is the only free equation, free function here. And Q is a function of U and the angular variables. The dependence on R is already determined by this condition here. So this condition strongly restrains the metric to this form here, mainly on air dependence.
The equation, the last equation.
The last equation.
So that means that Q is not a free function. Hold on.
Q obeys this equation. The rich flat condition implies
okay.
this equation.
Okay.
Okay, so this is the only dynamic equation that we have in Robinson-Trautman spacetime. Nabla square is the Laplacian on the sphere. The Laplacian on the sphere with respect with this metric. Okay, good. So we have the Robinson-Trautman equations. They describe a compact object surrounded by gravitational waves. I will explain this a little bit more in detail. Let's take some specific case. For example, the case that Q is constant. If Q is constant, K is also constant, Q square. And it's easy to see that we have Schwarzschild equation up to some rescalings. No? If Q is constant, this term is absent. And we have here Schwarzschild equations, Schwarzschild solution in some radiation coordinates up to some rescalings here. Okay. There is another thing that we can infer directly from this equation. This quantity is zero. I mean, this integral is preserved, okay, along the evolution. So if it's preserved, we can fix some value for it, and we will choose to be for pi, because in this case, we can identify as the area of the submanifold that corresponds to R equal 1 and U constant, okay? This is the, again, is this part of the metric. This here is stating that the area of this submanifold for R equal 1 is 4 pi. The asymptotic evolution of the Robinson-Trautman solutions is well known. In particular, for any reasonable initial condition, the evolution tends towards the stationary limit. The stationary limit here is this one. Stationary means that doesn't depend on U, so the stationary limit is this one. It's easy, it's a simple exercise to see that if a function that's constant obeys this equation on the sphere is constant. So the asymptotic evolution is K constant. What is Calabi flow? Calabi flow is exactly the same equation, but when you consider this metric from an intrinsic point of view. We are considering here this sphere as a submanifold of a four-dimensional space-time. So we are writing this equation using essentially no intrinsic geometric quantities. If you write this from an intrinsic point of view, this is easy to do. You can write this in this form where G is the metric for the sphere, and you have this condition. This is the Calabi flow as the mathematicians write. For our case, I will keep the formulation in terms of the Robinson-Trautman variables because it's easier to. It's a constant, nothing. It's a constant only to have the right dimensions, things like that. Okay. Kappa can be 1. Okay. So the Calabi flow or the Robinson-Trautman equations, if you prefer, is an evolution problem where some function is given, some initial condition is given, you need to solve this. Okay? This is a parabolic-like equations. If you start with some Q, that is a function of the angular variables, it means that that surface is not homogeneous. You have a kind of rugged sphere, a non-homogeneous sphere, and the evolution is such that you tend to uniformize this surface. You tend to have you preserve, and this is important. The evolution preserves the area and smooth out all the surface. You finish always with a perfect sphere. Okay, this is the essence of the Calabi flow. This is the essence of the Robinson-Trautman evolution.
So, Calabi flow is equivalent to
Yes, yes, it's the same thing. And they were discovered in almost the same year by Calabi, the mathematician, and Robinson-Trautman, the physicist. So we always finish with a K constant, Gaussian curvature constant, and the area is invariant along this evolution. Okay, if Q is constant, we know that K is constant. But there is some subtle point here that you can have K constant with Q non-constant. It's easy to show that K constant have this solution, where you aligned the coordinates in a convenient way. And we know that without this Q1 here, this is Schwarzschild solution. The question is, what is this thing with this Q1 here, not 0? Well, this is Schwarzschild solution also, but it's Schwarzschild solution in another set of coordinates. You need to interpret this new set of coordinates. There is some literature about that. It's missing some part of the paper. This is the paper where this is discussed. And you can see that with this Q, that corresponds to a Schwarzschild solution with some deformed two-dimensional sphere, this solution is asymptotically flat, and the solution has bounding momentum. If you go to infinite, you can definitely check that the solution has bounding momentum, non-vanishing bounding momentum. No, it's not Schwarzschild. This is the point. No, Schwarzschild is another set of coordinates. Look, how to construct a solution corresponding to a boosted black hole? You make a change of coordinates. Only this. Only this. It's only a change of coordinates. Okay. This has bounding momentum. A good interpretation for this is that this corresponds a black hole moving with constant speed. Okay, it's a black hole moving with constant speed. This is, of course, a little bit more complex than I say, but you have everything described in this paper. Okay. Another important point in Robinson-Trautman solution is that when this Q depends on U, when this quantity is not 0, you have the so-called Bond-Lewis function, and this is always connected to gravitational waves. The solution has a future horizon, so a good interpretation is asymptotically flat. So a good interpretation of the solution is that you have a compact object surrounded by gravitational waves, and these gravitational waves are going to infinite. And you end always with a Schwarzschild solution. Perhaps a Schwarzschild solution in constant moving with constant speed. This is the classical interpretation of Robinson-Trautman spacetime.
One thing that I would like to ask is that this kind of Calabi since it is vacuum, I would think that you could change the coordinates where you have spheres.
No. This is not the only change of coordinates. Change of coordinates is the final stage where you have a sphere, but in new coordinates. this is not only a change of coordinates. Here, there is some intrinsic physical data here. And of course, if you want to interpret the initial condition of Robinson-Trautman equations, the initial condition corresponds to a space-time that already had some gravitational waves there. Okay? This is non-stationary. This is non-stationary.
I understand that, but if you do universe content,
Yes.
what I'm saying is that you can always find a method of this sphere.
No.
So there is something there that I don't know of the sphere.
No, no.
Now I can go to coordinates where everything is.
No, it's not true.
No?
No, it's not true. You can find a coordinate system where this can be undone, but not a generic function. But not a generic function. Okay? Okay. So we have a question here. And the question is the following. We have Calabi flow that I said that is a quasi-parabolic equation with this funny evolution. And the question that was asked by David with the same T-shirt. The same T-shirt. Yeah. My T-shirt. The question is, how can the Calabi flow, a parabolic-like PDE, be equivalent to the hyperbolic-like Einstein equation? I hope that this is good English, because I'm sure that David asked in perfect English. But this is my remembrance of this, the question.
And he asked that photo.
Okay, the answer is because the Robinson-Trautman equation is a kind of restricted version of the general Einstein equations. This constraint is too strong. Of course, if you put as a hyperbolic set of equations, if you set the function and the time derivative of the function, this condition will not be kept along the evolution. The only way to have this condition along the evolution is that Q satisfy this equation. Okay, this is a critique on the Robinson-Trautman space-time. In fact,
what do you mean by evolution? You have Einstein equation, you have a solution. There is no evolution.
No.
Space-time.
No, I'm talking another thing. If you start with the full Einstein equations, with an initial condition that is the metric with this form and some given Q. But for the full Einstein equation, you need also to specify Q dot. If you do that, the metric will lose this form along the evolution. Okay? When you enforce the metric to have this form, that's equivalent to enforce the existence of the expanded congruence, blah, 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 then Q must obey this equation. This is a subset of the Einstein equations, and there is some discussion if it is realistic or not. I think that while you are restricted to vacuum case, this is realistic. If you allow, for instance, some electromagnetic field, there is a lot of doubts here. Cosmology is not a problem at all, but electromagnetic fields, yes. Cosmological. There is a problem with cosmological constant that I will talk with the 2+1 case.
But isn't rational family of solutions also part of the Robinson-Trautman?
Yes, but
so you have to change.
No, but this is exactly these solutions are known to be unstable. Unstable. If you force something equivalent to this, to the case with electrical charge, then you have unstable space-time.
That's why it's not unstable.
Robinson, okay, Robinson itself is the inner horizon has some problems.
Is it because we
No, the problem with Robinson-Trautman is not this. It's another problem. But I'm talking about the Eisner-Nordstrom black hole has its own problems with the inner horizon, things like that.
What's your study? Can you say something about how restrictive the assumptions are in building this? So I would interpret twist reasoning is basically no angular momentum.
Yes.
So it's not protected. And vanishing, so within that class then, if I even restrict that to something, how bad is vanishing shear as opposed to as an assumption?
I think that for vacuum solutions, it's not a big problem. But if you allow for electromagnetic radiation, you always have some shear in the congruence of the medium. But I think that for a vacuum case, it's not a big problem. I think more than that. I think that for vacuum case, you can show that the shears in a asymptotic flat situation, the shear tends to zero when if you start with some crazy initial condition, the shear dissipates. Yes, but I'm saying that if you start with a generic initial condition, the shears will dissipate. I think this is a result, but I need to check. For a asymptotic flat case in vacuum, vacuum is crucial. Okay? If you have any kind of matter or everything is okay. So now about Robinson-Trautman arbitrary dimensions, this is well described in this paper, the motivations, why people are interested in this kind of questions. I will not talk about these things, but the point is that for any bigger than 4 or higher dimension, there is no big problem. So everything here can be generalized quite easily. These conditions now implies that the metric has this form. You have the vacuum solutions now. Vacuum solution here is equivalent to more than one equation, but anyway, the evolution problems is more or less the same. If we start with some generic data that correspond to the metric of n-2 submanifold, and the evolution problem is just that this goes to some intrinsic curvature constant, and you finish with some n-dimensional Schwarzschild. Okay, almost everything that we have in the 4-dimensional case is preserved for the higher dimensional case. Of course, there is some difference because you have this thing like peeling theorem that are different, but the structure of the equations is almost the same. Okay, and now why 2 plus 1 is different? In 2 plus 1, I can also impose that Singdus. Okay, why 2 plus 1 is different? We can see this equation, try to put n equal 3 here. Why is different? The question is that in 2 plus 1 dimensions, the rich tensor determines completely the Riemann tensor. In particular, H flat in 2 plus 1 implies flatness. So this is well known. In 2 plus 1 gravity, you can have only curvatures like delta functions. You cannot have curvature in the vacuum case, of course, because the Rich flat conditions imply that the space-time is flat. So there is no Robinson-Trautman solution in 2 plus 1 because 2 plus 1 is trivial for vacuum solutions. This is the idea. However, we know that there is a 2 plus 1 stationary black hole. It's the BTZ black hole. It's not asymptotically flat black hole. It's asymptotically anti-de Sitter. But this is not a big issue here. And the question is that it would exist some kind of 2 plus 1 solution that would mimic the main properties of the Robinson-Trautman spacetime? And the answer is yes, of course. How to do this? We start with the same constraint that you want that the spacetime has this set of null geodesics, but now you relax the vacuum condition. You allow for vacuum solutions. All solutions, the Einstein equation in 2+1 dimensions are classified. You can check in this paper, they are classified. So we can take the form that is more convenient for us. This is the best way of writing this equation, that the metric for Robinson-Trautman 2+1 that is compatible with the first constraint. But now we have some, it's not vacuum anymore. So we have energy moment tensor. In particular, the energy moment tensor has a UU component that corresponds to a kind of null fluid with this aspect. Okay, and this funny combination can be interpreted to one-dimensional Laplacian. This is something curious. You can define a one-dimensional Laplacian on the circle. And now we will repeat almost the same steps that we did in the Robinson-Trautman in 4 dimensions. I will demand that this quantity is conserved. This quantity here, if you remember the method, this quantity is the length of the circle, topologically circle, that is parameterized by this phi. So this is the length of the curve, because it's a supermanifold of a 3-dimensional space with codimension 2. This is a curve. Okay, this is the length of the curve U constant and R equal 1. And I will demand that this is 0. If I demand that this is 0, if I impose that this is 0, then we will have some kind of evolution that preserves this length. Okay?
M0 is not negative.
What is negative?
M0.
M0. I think it depends on the conventions that depends.
It is a bit negative.
If it is negative, but I need to check the signs. Then I don't remember. Okay, but of course, to be BTZ, this guy and this guy must have different signs in order to have a 0 here. Okay. I will impose that this is 0. So we have some easy possibility, that is to impose that P here is the equivalent of Q that we have before. But in this here P is completely free. Okay. For any P, if you substitute here P and P here and here, this combination satisfies the Einstein equation in 2+1 dimension. So P here is a free function, and the idea is to impose an evolution for P that will be able to mimic the main properties of the Robinson-Trautman evolution. Okay, the first possibility is to write this simply in this way. We have this equation. This is a very simple equation. It's easy to see that you start with some generic P and tends towards a P constant. That's the circle, and being a circle, this is the BTZ black hole. If you take P constant, then this term disappear. I think that is right here. This is the minus. Okay. With this constant, this is BTZ black hole up some rescalings. Okay. The question is that it would be more interesting to have not P constant, but P as an ellipse. Why? Because ellipse is what we had before. And perhaps this is more complicated, but we could interpret this as a boosted BTZ black hole. This is much more complicated because the interpretation of the Robinson-Trautman solution as a boosted black hole depends on the asymptotically flat vision, because you need to read this bond, the moment, and things like that. There is nothing equivalent that I know for the case of asymptotically anti-de Sitter case. There is no, of course, there is BMS group for the Sitter, but it's much more complicated to read the physical information. But of course, that there is the equivalent of the BMS group for asymptotically anti-de Sitter spacetimes. So the simplest choice in linear ellipses is this one. Okay. If you compare with the previous case, there is a lot of similarities here. In particular, this can be formulated as a theorem. You can show that this is the unique fourth order derivative quadratic and net preserving operator. This is the unique operator that fourth order derivative quadratic in P and is compatible with length preserving of the evolution. So my claim is that it is the best candidate to be the equivalent of the Robinson-Trautman or Calabi flow, if you prefer, in 2+1 dimensions. Okay, I call this one-dimensional Calabi flow between between quotes, because there is no Calabi flow in one dimension. Okay, because there is no intrinsic geometry in one dimension. Okay, the asymptotic evolution of this equation is this one. This is the stationary limit of this equation. In fact, this is a deformation of curves that tends to ellipses. This is it's a problem of planar curve deformations.
So when you obey this one-dimensional Calabi flow from the Robinson-Trautman enzymes imposing a single modular constant and no more matter?
No, no. Unfortunately, no. Okay, I'm finishing with some final remarks. This is the equivalent of the Robinson-Trautman evolution or Calabi flow, if you prefer, in 2+1 dimension. This is again an evolution problem. You give some initial condition, some function p, and the idea is to obtain p as a function of u. We know that the asymptotic evolution of this system is towards this solution. Of course, that the hope is to interpret this a kind of walking BTZ black hole, but it's much more complicated, okay, than the other case, because you don't have the equivalent of the bond momenta and things like that to be sure that that solution corresponds to a black hole that's moving. Of course, there is a lot of problems yet to be solved. First is the physical interpretation of this boosted between quotes BTZ black holes, not clear that they are really boost. Even the problem of a boost solution in anti-de-Sitter spacetime is not so easy. In anti-de-Sitter spacetime, a boost solution can be a solution, a circle, for instance, because the geometry of anti-de-Sitter, the geometry of anti-de-Sitter spacetime is strange. Of course, there is no hope in solving this equation analytically, so we need to propose some numerics to do this. This equation is prone of a lot of numerical instabilities. The idea is to use some kind of Galarkin methods, search for conservative quantities. Okay, there is a lot of things that can be done here. That's all. I think it was 40 minutes, yes? Or not?
It was
40 minutes.
40, yeah, 40
Yeah,
minutes.
so-
40 minutes. Yeah. Good job. Yeah, please.
Thanks for the seminar. Thanks for taking me to my supervisor language would say, your seminar, you have to give your seminar, and if you give your seminar with less time than are expected, everyone's going to be happy. If you take more time, nobody likes it.
This is very important. It's very important for PhD defenses. People, the students must be this.
And I have a question. Do you have gravitational waves here now?
No, you don't have gravitational waves, but you have some fluid waves because you have matter here. Huh? If you
Cosmological constant.
no, not the cosmological constant. If you recalling here the energy momentum tensor, yes, the energy momentum tensor, you have some component, non-vanishing components that depend on P. So you have some kind of new fluid here. You have radiation because it is a new fluid, but it's not gravitational radiation, right? Because we are in 2 + 1 dimensions. There is no room for gravitational waves here.
But it is, you have cosmological constant, so it's RAB is equal to lambda or lambda plus TAB.
No, lambda is in the other side here.
It doesn't matter.
Yeah.
Lambda can put in everything.
Sure. No, this is
RAB is equal to lambda plus TAB or what? Yes.
this is
put lambda,
yes.
that's the question.
yeah. This is only the matter content, and the lambda here is not considered as a matter. If you want, you can sum here lambda if you prefer.
Yeah, but not vacuum solution. The RAB is equal to dependent.
No, it's not vacuum solution.
But it's a cosmological constant. You have a lambda there, right?
Sorry, I understood. So this must be Einstein tensor minus vacuum here. I mean that you have some component besides the pure geometric thing, and lambda is a kind of okay. Okay, but here vacuum means that you have something besides the lambda.
You say that you include I wasn't 100% sure. Is this a physical restriction or is this vague or something? This is restriction on this form of the percentage tensor. What does that mean?
This is a kind of gauge restriction. Really, I think that this is nothing you change if you rescale P by some value of some constant. So the idea, first thing, that this is preserved, this is a condition that Robinson-Trautman had, and we have to impose here. The exact value of this curve, the length of this curve, this is irrelevant. This is irrelevant. Yeah, this is at the end, this will be a rescaling. It's not a problem. But the fact that this is zero, that this is preserved, this is a property of the Robinson-Trautman spacetime that we want to mimic here.
But the solution is singular, of course.
Singular in R equals 0.
Your solution is zero. You use 1/r. So.
No, see, yes, this is spherically symmetrical. Yes, this is the usual divergence that you have in all spherical symmetric situations. The origin can be. Well, okay.
Yeah, but if you have a horizon, it's fine. Everybody say, okay, it's inside.
We have a horizon. Yes, the idea is this. The idea is that the end point of this evolution, that is BTZ black hole.
But, okay, the BTZ black hole is a topological curvature. Very curvature. Doesn't matter.
No, that's total case. This go to 0. Yes, in the asymptotical region, this n goes to 0. But if we stop before, for some finite u, this is a singularity inside the black hole, and I didn't think about that.
Well, it has to be always there.
Yes.
I don't see how you can change curvature singularity to a topological singularity. That is topology. RAB is equal to 1 for the whole space-time. So there is no curvature topological singularity.
Doesn't have to be that, right? Nothing else that is to be there.
No, that's what I'm telling you.
No, the idea is that it should be BTZ. So, but there is a BTZ is a kind of central singularity. I don't know. I need to think about that. The exterior region is BTZ.
Yeah,
that's for sure. The exterior region.
So don't you want to impose the existence of trapped surfaces so that there is a horizon? Like that's a further condition that you can impose on people.
Yes, yes. This is not enough to mimic the Robinson-Trautman evolution, I guess. This is not enough.
Yes, but it's not enough. So
Yeah. No, yes. Yeah.
Any other questions? In that case, maybe I can ask a very naive question. So you mentioned that that the case n equals 2 + 1 is different. I wonder if it is of any relevance to consider what would happen in the case n 1 + 1, because that means that term that you were referring to that changes. It's kind of quadratic. I don't know if that's any relevance or.
N equal 2 + 1 in the sitter. What happens that reach flat will not imply Riemann flat because you have cosmological constant. So what you have that if it's reach flat, you have a so-called homogeneous space where all the sectional curvatures are lambda, things like that. It's an important point. Reach flat implies Riemann flat only without cosmological constant. If you have cosmological constant, not even what is Ricci flat. You don't have to see.
Any more questions?
Just the point is here that in the four-dimensional case for triple one, so here determined by the Einstein equation of Calabi down below. So here B cannot be determined.
Not, yes. I propose, I invented the evolution.
Okay. So my question is, the E enters there in the energy momentum tensor, right? So is that energy momentum tensor divergent free?
Yes,
Okay.
sure.
And
Yes.
that is regardless of the thing.
Yes, yes,
Okay.
yes. Some miracles, yes.
I just understand that, like, the divergence free of the energy momentum tensor is the
No,
equation.
no.
So, just for curiosity, but going back to the arbitrary diagram, please go back to
Which one?
yeah, solution in the
I
N
think
plus.
some before this
N
one.
dimension.
Before? No,
Before.
before is this one.
It was before you said n equals 2 plus 1. Yeah, that's the
Okay,
one,
so
right?
when you replace, for example, N minus 2 sphere to be some flat space or N minus 2 dimensional hyperbolic space, but can you still have
I think not possible. When you impose this condition, this submanifold must be compact. Not possible to have. You cannot have a plane, for instance. When you put this condition, this submanifold is compact. It's more than this. I think that is in the four-dimensional case, it's topological sphere. You cannot have a torus, for instance. I'm not sure, but I think that you can prove this invoking Poincaré theorem. That's famous Poincaré of the spheres. You can use this to prove this result. That when you impose this condition, now is Poincaré per element. Yes, this is a sphere.
If you enjoyed the video, like and subscribe.